Hello, this is Joe Barr, VP of Research at Acronis SCS and a Director of the MI Lab. I'm going to talk about on unbalanced data empirics to simulate minority examples. This work was done jointly with Marcus Sobel of Temple University and Tyler Thatcher of Acronis SCS. The agenda. We'll talk about binary classifiers, balanced and unbalanced data. And then we're going to discuss the case study, which is analysis of the Android OS source code. We're going to talk about signal amplifications, the three approaches, naive upsampling, bootstrapping, and SMOTE. And the key words here are binary classifiers, unbalanced data, upsampling, and SMOTE. What are binary classifiers? A classifier estimates the conditional probability that the tag y equals to +1, given some vector x, the feature vector, regard the probability of y equals +1 given x as the score, which is based on training pairs, x and y, where x is a vector of features and y is a binary tag, which equals to two possible values, say +1 and -1. To learn a binary classifier, it's necessary to possess a generous fraction representing each class. Practicality determines what might be regarded as generous. However, in general, if fewer than 5% of the minority class are present, then we'll consider the data as unbalanced. If more than 5%, then the data is more or less balanced, although perfectly balanced data is one where the split between the two classes is more or less 50-50. However, this is a long continuum, so we take this somewhat arbitrary approach that if it's fewer than 5%, it is considered as unbalanced. And unbalanced data poses a problem when using a classifier. Therefore, the signal must be amplified somehow, and this is what we're going to talk about. In our case, and again, it's somewhat arbitrary, we regard the class that is labeled as -1 is good, and the class labeled as +1 is bad. Of course, one may choose otherwise to label the good as -1, the bad is -1, and the good is +1, but it's completely arbitrary. In our case, we have too few bad examples. Unbalanced data is commonplace in the study of phenomena where data is heavily skewed toward what you might regard as normalcy. This is often found in the study of consumer behavior, marketing, socioeconomics, credit. Also, when you study social pathology like crime and fraud, and also the study of disease in medicine, in healthcare, where the common or the normalcy is not presence of certain condition, and the abnormal is the presence of the certain condition. In all those cases, unbalanced data is common. And it's even not uncommon to study good versus bad, where the majority of good consists of more than 99% of the records, an exceedingly small minority are bad, less than 1%. In fact, we'll show that in our case, the situation just described, where more than 99% of the data is good and less than 1% of data is bad, is in fact very, very common. In our case, we consider the Android operating system as our case study, as the data. The bad examples are those that are tagged as vulnerable. In other words, if you have scanned the code, the source code, then you would have found evident problems in the data, and you'll consider those pieces of code as vulnerable. Otherwise, you wouldn't consider them as vulnerable, although they might or might not be. We simply haven't put the resources to scan the entire code base. As we'll see, Android is a rather large corpus of data. There's a data known as the Common Vulnerability Exposures. It's a database. It's publicly available, owned and managed by the MITRE Corporation. And this is considered as the gold standard for what is considered as vulnerable. Vulnerable in the sense that it's open to hacking or malware in our case. The data that we study is based on an extremely large number of good, 99.5%, is not known as vulnerable, and we make the assumption that it is not vulnerable, and approximately 0.5% are non-vulnerable. The particular unit we decided to take, or the records, are the code functions. In other words, functions that have parameters and do something or return some value in the normal execution of the code. The Android database consists of approximately 1.15 million functions, of which approximately 6,775, actually precisely that number, are tagged as vulnerable. That is approximately 0.5% of the 1.15 million are tagged as vulnerable. We go through a long process of appending features to each function. Some of those features are known to be called auto-encoded. That it's a technique that uses neural networks to encode automatically 128 features. And then we also cherry pick 4 particular features which are based on the idea of code smell. Not going to go into that, but a totality of 132 features. So if you think of it, we have 1.15 million records, and each record has 132 features plus an appended tag, good or bad, based on whether or not the function is a known CVE. And you can visualize it more or less. Of course, it's not faithful to scale, but the matrix, if you think of the X as the features and the Y as the tags, if you have 1.15 million functions, the matrix will have 1.15 million rows, and 132 plus 1, that is 133 columns. So this is certainly, this picture doesn't faithfully represent it, but at least it gives us an idea of the shape of the matrix. We compared 3 approaches, and all the 3 approaches consists of a workflow that has include upsampling, the modeling, the classification, which is the statistical model, of predicting the probability of a tag +1. And finally, testing. Testing is done against a data that the model hasn't seen yet. For part 2, the modeling, we use a garden variety gradient boosting algorithm to estimate the score, and I denoted like p hat of x. X is the feature, which represents the probability that y equals to +1, given the feature value x. For part 3, we stick with tradition. We calculate 2 metrics just to make it simple, although we can look at more metrics. We look at the receiver operating characteristic, or ROC. Specifically, we look at the area under the curve, or the AUC, and we also look at the lift. And the lift is a common metric which represents at every level the percent of positive tags up to that level as a function of the score. And we do that, of course, in the testing against holdout data or validation data. So the parameter here is the first part, the upsampling, and we use 3 different techniques for the upsampling, and we compare them. So first we use what we might regard informally as naive upsampling. The second one is bootstrapping, where we randomize the selection of the data under certain parameters. And the third, we simply implement an algorithm that is known as SMOT, or synthetic minority oversampling technique. Let's start with the naive upsampling. We call it naive because we make no further assumption or any further provision, special provision, with the exception to, in every upsampling, we take a fixed number of positive from those that are available to us, the 6,700 some. And then we take randomly select an equal number of negative examples that we have in abundance. So we end up with 10,000 training pairs on which we build the model and test against the remaining roughly 1,500 positive, that is CVEs, and an equal number of randomly chosen negatives from the plethora of negative examples. And we did so, and as you can see, we checked it against the ROC, the receiver operating characteristic, or upsampling. And the area under the curve of the ROC is 0.92, almost 93%, which doesn't seem so bad. Can we do better? In the bootstrapping was introduced by Brad Efron more than 40 years ago, that strive to resample from the data, calculate a metric, and somehow smooth it out, like averaging it out, whereby creating a more robust estimate. So we've done it against a sample of 80% bed. We fix the percentage of the bed, not the numbers. So we repeat the experiment each time. We sample 80% from these 67 odd hundred beds, and we sample at random a similar equal number of good, and repeat the process 100 times. In each iteration, each one of those 100 times, after we sample, we build a model, then we test the model, and in fact, report here AUC and also the specificity, which is just true negative over those that are really negative, and the recall, which is the true positive divided by the predicted positive. And what we noticed that the AUC here gets a little better from what we had before, somewhere between 96 and 97%. It's been pretty stable. Synthetic minority oversampling technique, SMOTE, is an interesting idea. It's not very complicated, but it was published in 2002 by a group of researchers led by, or including someone named Chwala et al. The paper is cited extensively, and the code is publicly available on public repository like GitHub. And the SMOTE simulates new minority examples similar to those that are known to be the minority example. So the process involves appending the, those are known as positive examples of minority, by simulated positive examples. And the parameter is how many positive examples need to be simulated. Typically, it's between 5 and 40%. Of course, there are infinitely many numbers between 5 and 40, but if you think of it as increment by 5, then you only need to do it 9 times, or 8 times, in fact. And we use original data to test the model. So we don't like to test it against the simulated positives because we might not get what we really need. And in fact, we have simulated it against levels 5, 10, 15, 20, and 25%. We notice there's no need to go beyond 25%. And at each instance, we have calculated the ROC for that level, and we noticed that the ROC or the AUC are very, very, very similar, all hovering about 95 to 96%. In fact, at level 10, 15, 20, and 25, they're almost identical at just below 96 or at 96%. But we noticed that in our case, the 20% upsampling yields best results. We're also interested in the metric which we call lift, and lift is simply a model of efficiency to detect positive tags, because the positive tags are those who are predicted to be vulnerable. And we're interested specifically in those. And those predict how many we can catch at the high end of the spectrum, so that the probability of being a vulnerable function is high. And the lift measures it against the uninformed predictor, which is just the diagonal line in the picture. And we have the lift at various levels of SMOTE. And we noticed that at 20 and 25%, they are virtually tied at 84.8 to 9, almost 85%. That is the discriminator of the model. against an uninformed predictor, say a coin flip, is at almost 85%. Thank you.